Okay, so this is the second part of our series or of our talk, whatever you want to call it, on measurement methods for mechanistic force-based spinal manipulation research. And I'm going to talk about some tools that are available. I want to stress up front, this is not an advertisement in any way. I do not endorse the products. I just am aware of them and wanted to make you aware of them. So before I do that, I just want to give you a quick introduction to how an engineer thinks about biomechanics, or at least how this engineer thinks about biomechanics. It may be different from how some of you think about it. This presentation was originally given primarily to chiropractors, so it's a very different background. And I want to make sure that you understand why I say some of the things I say and how I'm thinking, so that if you find it uh, inconsistent with your own views, it's probably because we come from different backgrounds, and that's something that is that's an opportunity for improved communication. So to get to the point, when an engineer thinks about biomechanics, the first thing we think about is Newton's laws. The force is equal to the mass times the acceleration. An object in motion tends to remain in motion, and an object at rest tends to remain at rest unless acted on by force. That's how we want to think of this problem, right? We want to think about it in terms of forces and in terms of accelerations and the velocity in the position. There's the integrals of the acceleration or other measures of position. And we want to think about how they relate to each other. And I want to make a quick aside on reductionism here, because I think it's important that when I look at a problem, what I want to do is break it up into as many little parts as I can that I can analyze easily. And then we eventually reassemble them all into the whole thing. But I want to look at every unit or every segment of the body separately and analyze them under their own set of rules under Newton's laws. And then I can come back later and figure the whole thing out. So that's going to talk a little bit in the final presentation on sort of thinking holistically, but for now we're gonna think a little more reductively. I also want to talk about when we think of a measurement. So if we're going to make a measurement on the body, I just want to make sure that we're all using the same language. I use the term kinematics to refer to measurements of motion without regard to what forces are causing that motion, and kinetics, excuse me, to refer to the motion with also thinking about what forces are involved. So if we think about kinematics, as I said, it's the study of motion without regard to the forces that generate the motion. It is a purely observational discipline, and that does not make it valueless. All right, I want to stress that just because there is no underlying physics involved, or being measured, we're just measuring the motion, that does not mean it's not a useful measurement. Range of motion and path of motion are both very much kinematic measurements. So how far can I move, or if I touch my nose, do I do it the same way every time, or do I go like this sometimes? Those are the kind of things that might be very useful information, but we just want to be clear that it is entirely observational information. Sort of the classic kinematics problem is gait, where people are trying to analyze how people move when they walk. So by far the most common tool for measuring motion kinematically, particularly in large systems like a person, is video tracking. It's very simple. If you're in two dimensions, so if you're moving in a plane, a single camera is sufficient. If you're moving in multiple dimensions, in the third dimension, then you need multiple cameras, and the software can get pricey depending on what you want. But smartphone apps are just emerging, and they keep getting cheaper and cheaper. I just like this picture. This is a guy with a bunch of dots on him. You take the video of it. This is for the Vicon system, and it will capture the motion, and it will track the dots as they move, and then that can tell you how the man in the suit is moving. There's a really interesting phone-based system. I have never used it. It's from Stanford. It's called OpenCap. It takes smartphone video from one or more smartphones, and it makes a model. And I have a video here that I think is kind of cool, so I'm going to show it to you. So this is a person going from sit to stand, and I'll show it again. And this was based on a video of the person. The skeleton in the video and the muscles that are drawn, those are all inferred based on previous models and analysis. There is no analysis of the motion other than, well, the hips have to get here, so the pelvis is going here. I do not know how well they can achieve anatomical subject specificity. So if you took me and Beth and took video of us both, I'm considerably taller than she is. It would correct for that. But would it correct for the subtle differences in our anatomy based on how we move? I don't know. Um, but I think if you want a fairly crude measurement of something that is relatively easy to measure, I think a system like this could be very valuable. You know, I've injured my shoulder. How far above my head can I get my arm now? I think simple range of motion like that, I think would be very easy to measure with such a system. But again, I've never used it. The Stanford group that produced this also has a computational tool for modeling motion of the limbs. That's what this looks like, where they have models of all the muscles. That's been a very long and successful program for a long time, but I don't know how well this specific system works. Oops, there we go. All right. They're so-called embedded systems. They're much more expensive. They are driven by the movie and video game industries. So you have a person in a suit, and the suit has sensors built into it. And then the person can move, and as you can see, it can track the motion, and it can make this funny video guy move, right? So here's the person in his suit, here's the motion track, and then here it is projected into somebody in some fancy armor for what he wants to do. All right, this is a much more expensive system. They're very nice, and you sort of have to have a suit for everyone who's about the same size. Someone who's a lot bigger or smaller would need a different suit. I think it's something to consider if you have a lot of money to invest and you have a project that's already very well established and you're trying to step up. I do not consider this an entry-level system just because of the cost. Fluoroscopy is a different way to think about kinematics. Some of you are probably familiar with it. It's basically an X-ray movie. So if you have two scopes, you can track motion in 3D. There are methods to do this. Aaron Ellingson from our Spinework team is an expert in this area, and I'm sure he'd be happy to talk to you about it if you're interested. It's very expensive, and it's not mobile, and you're exposing to people to X-rays, which is dangerous. But if you want to get the actual motion of the person's bones, where are the bones going, you can't beat it. It gives you that motion, and it measures it on the individual as the individual moves. So again, if you're thinking about what you want, what stage is your project, how much do you want to spend, fluoroscopy is very expensive, but it gives you something you can't get anywhere else. All right? The simple video-based motion captures that we started with are dirt cheap, if not free. They give you a rough idea of what's going on, but they don't give you this level of detail. So I think that's a fundamental message here is you want to do what you want to do. Here's a video from Aaron. So this is the two different fluoroscopes with a person just moving their head around. And this is a reconstruction of the cervical spine and how it moves as this person is moving. So here we can see, raise our head, do a little bit, come back down, and here's what the vertebrae we're doing. So you see you get a much, much more accurate representation of the motion, right? That you can't possibly get with just external video. Again, the downside is you had to spend a lot, and you had to expose people to X-rays. I just wanted to show briefly this little sort of chart that, excuse me, our imaging group developed, and it's a sort of a map of different technologies. And they have three scales: small to large, slow to fast, emerging to clinical. So fluoroscopy is relatively new. It's not terribly fast. It's not as slow as, say, an MRI. And it's sort of at intermediate scales. CT, X-ray are very well established. They're not terribly fast. They work at moderate scales. MRI gives you a little more variety. Maybe it's a little newer. It's still slow, but it can see other things. Ultrasound is much faster and easier. Again, fairly well-established technology. So this is just when you're thinking about technologies for imaging, if you want to measure things or measure motion, that I just thought that was a nice picture to help frame the conversation. So I wanted to have you see it. And I think the message here, again, there is no best tool. There's only a best tool for a given application. So depending on what you want to do, what you need will depend. And I think our imaging group is really good, and I'm sure that the people in it, in particular Aaron Ellingson and Simon Tang, would be very happy to talk to you about your imaging needs and how they would recommend pursuing meeting those needs. Okay. I'm going to switch briefly now to kinetics. So now we're talking about forces. What is the force that is acting, that is producing the motion we see? And the critical question here is, where do you want to measure the forces? So force plates, again, many of you will be familiar with these, are absolutely superb at measuring ground reaction forces, right? So they have 1 degree of freedom plates, which pretty much tell you what the force is vertically and where it's located. So this is essentially a souped up version of your bathroom scale. And then there are 6 degree of freedom plates, which can measure normal forces, shear forces, and moments. So 1, 2, 3, 4, 5, 6 degrees of freedom. They can give you a lot of accuracy. They can tell you very much what forces the ground is applying to the person. And so from there, we can figure out what we want to do. There are also various handheld devices that can measure unidirectional forces. So if I poke at something with the device will tell me what force is acting on it. And again, if that's what you're trying to measure, there are some very nice devices that do this. They're used sometimes to try to make estimates of tissue properties from just poking the person. Obviously, there's some inaccuracies in that because the person is more than just one big blob of tissue, but they can give you some nice information. And then there are some fancier things. So these are hand force sensors. So this is a TechScan product. This is a Novell product. Again, I do not endorse them. I am simply aware of them. And these will give you forces being exerted on the hand through these sensors that are then attached to a recording system. So now we're starting to measure what are the different forces being involved in the gripping or in the opening of the hand. It's just a slightly more sophisticated and more accurate thing than a force plate. And of course, it works on a person's hand. So if you're interested in measuring on the hands, there you are. I wanted to show this because I think this is really an interesting concept. This is also from Novell. And again, I do not endorse them, although I will say they were very nice to send me this advertising video that they had made. I'm not going to play the sound, but this is a fabric sensor. So it's a piece of fabric. It's similar technology to the stuff in the whole body suit. It's a force sensor that is built into a fabric. And this guy is going to do it. He's going to perform manipulation on, I think this is a real person, and we're going to see the force recorded in real time. So here he's got it. It's just like a piece of fabric. These run about $5,000, so it's not dirt cheap. But again, if you want it, it's going to do what you want to do. If it can do what you want to do and you don't have anything else, it's what you want. So he puts it on there. As he pushes, you can see as he makes a thrust there, you see the force go up. So this is a very interesting new technology. I think that it can really be helpful, and then he's talking now about how you can analyze the results. I also think every single piece of technology that I talked about today is going to get cheaper and cheaper as time goes by. As people continue to improve the methodologies and the instrumentation, it's only going to get cheaper. So I would not, in general, consider myself limited by the technology. If you're limited by the technology, in 5 to 10 years, you probably won't be. So I would encourage people to think fairly aggressively. This is also a convenient time for me to mention that we have a small grants program that can support purchase of technology up to a few $1,000s with some justification as it's a seed for a larger project. So that is the end of my talk. I hope that you enjoyed it, and I hope that you find it useful. If you have questions, please contact Spinework. And at this point, we're going to go back to the next video.